Are your designs limited by tight space requirements? Does it run on batteries that require charging? Does the drop in output voltage as the battery drains cause problems for your application?
Then I have good news for you. Today I'll show you the nPM1100 evaluation kit. It features the first ever power management IC from Nordic Semiconductor, the nPM1100, a really compact PMIC for small battery-powered applications. So let's see what's inside this box. I got this anti-static bag, and inside it is the nPM1100 evaluation kit. And this component here is the nPM1100 PMIC, Nordic Semiconductor's first standalone power management IC ever. So what's so special about this little guy? Well, as I just said, it's a little guy. Measuring only about 2.1 by 2.1 millimeters, it is the smallest component we have ever launched to date. If you have a small LiPo or Li-ion battery, this guy will charge it. And if you need 1.8, 2.1, 2.7 or 3.0 volts of regulated voltage, this guy can deliver up to 150 milliamps of it, all while still being incredibly tiny. It is actually the size of about only 2 grains of uncooked rice, depending on the species of rice, of course. It also features LED drivers for charge state and error indicators, and a ship mode to enable even lower quiescent currents and disable power output, which means you won't need to integrate a separate power switch in your design for applications with a long shelf life or for shipping devices with a pre-installed battery. And it's of course compatible with USB power, with port detection for automatically setting the compatible input current limit, or any other 5V DC power supply. It is also extremely efficient at regulating power, up to 92% efficiency with a big inductor and 88% efficiency with a smaller inductor, allowing board space usage for the PMIC and its passives to be as low as 23 square millimeters. On the EK though, we use a big inductor for the highest efficiency possible, so here the footprint is about 27 square millimeters. To get started with the EK, you first have to do one thing: peel the plastic protection off of the dip switches. This switch sets the mode of the buck regulator. With the switch in the VSys position, the buck regulator is in automatic mode, which allows for automatic switching between hysteretic and PWM mode, depending on the load. Hysteretic is more efficient for low loads, while PWM is better suited for high loads. If you switch it to the ground position, it's in forced PWM mode, which allows for output with less ripple and lower noise, regardless of the load. This is useful for applications with wireless transceivers, which could be affected by electronic noise from the switching regulator. This switch lets you set the VBus current limit on the PMIC. This position gives a static 100 mA current limit, and this gives the full 500 mA limit. If powered by USB, the switch should be in this position to enable the integrated USB port detection. This switch switches between the two termination voltages of the charger, 4.1 or 4.2 volts. Please check the charge level limit of the battery you're using prior to setting this, to avoid damaging the battery. This dual dip switch package lets you set the output voltage of the buck regulator. 2 switches gives 4 binary combinations for either 1.8, 2.1, 2.7 or 3.0 volts. Refer to the user guide to find the combination that gives the voltage your application desires. And the last, but certainly not the least of the dip switches is this 5-switch package. It regulates the charge current of the battery charger. Which switch gives what current is easily found with this handy diagram right here on the middle of the board. Setting one and just one of the switches to the on position, as showed here on the side, enables the current corresponding to that switch. Combination of switches are also possible, just remember that you'll have to calculate the resulting resistance as a network of parallel resistors. Then the charge current can be found by solving this equation to find I. You could also leave all the switches in the off position and solder a resistor with your chosen value to the solder pads here marked R12. There's two LEDs for charge and error indication here, and on the other side there's buttons to enter and exit ship mode, which also disables and enables power output like I told you earlier. Along the sides here you have headers for all the pins on the PMIC itself. These allow you to control all the selectable settings on the nPM1100 from GPIOs on a SoC. That allows you to test different settings without having to physically change the switches. On the top we find 3 different types of battery connectors, one for batteries with a separate thermistor lead that takes advantage of the PMIC's integrated battery thermal protection, and 2 for 2 leads batteries without a battery thermistor. A micro USB port is found here, or you could connect any 5V DC power supply to the VBOS pin right here. These headers are for current measurement. For that you could use the very sought after Power Profiler Kit 2 from Nordic Semiconductor. A boring old regular ampere meter or an oscilloscope in combination with a shunt resistor would also work. The user guide contains a guide on how to set this up. The PMIC is already in full volume production with samples and EKs available through our distributors. If you want to learn more about the evaluation kit, go to nordicsemi.com/npm1100ek.